Welcome to AI Paper Podcasts. Today we are diving deep into Kling-Omni, a generalist generative framework for unified video intelligence, or as it's being called, Kling-O1.
And our mission today is really to unpack why this paper is such a big deal. It's a foundational shift in how video AI is being approached.
It really is. It feels like this paper is declaring war on, well, fragmentation. For so long, video AI has been this collection of separate, specialized models.
Exactly. You had one for generation, a different one for editing, another for understanding. Kling-Omni just says, no, we're building one unified system that does all three.
And the innovation that makes that possible is what they call the Multimodal Vision Language Paradigm, or MVL.
Right. And this is more than just combining text and an image. It's about treating text, reference images, even video clips as a single cohesive language.
A language that guides the model's creative intent.
Exactly. Architecturally, the whole thing is built on a unified diffusion transformer, and it's tightly integrated with a multimodal large language model and MLLM for the reasoning part.
And this is where the engineering side of it just blows me away. They achieved a 15x inference speedup.
It's massive. They took the number of function evaluations, the NFE, from a pretty standard 150.
Down to just 10. That kind of speed completely changes the game for actually deploying something like this.
And that speed, plus the MVL paradigm, lets Kling-Omni get these state-of-the-art results on tasks that other models really struggle with. We're talking complex referencing, interactive editing.
And generation that's actually enhanced by reasoning. The human evaluation showed it significantly outperforming models like Runway LF and VO 3.1.
Okay, so let's unpack that core vision, because the paper frames this in a much bigger context.
They see it as a step toward AGI, right? Towards these multimodal assistants that can perceive, reason, and create across, well, all our senses.
Exactly. And if you look at the field right now, the biggest bottleneck is always trying to get video understanding to work with video generation.
Mm-hmm. Most state-of-the-art models are super focused. Maybe they're great at text to video, but that's it.
And if they do offer more like image referencing, it's usually through these clunky separate pipelines or external adapters. It's not truly integrated.
And that separation is what stops you from doing really advanced, flexible things. You can't give it interleaved instructions.
Right. You can't just say, generate a stormy beach, but use this image for the waves and make the dog from this clip run slower. That's too complex for separate systems.
Because a simple text prompt just can't capture that level of visual nuance.
It's just not efficient for it. I mean, try writing a prompt that perfectly describes the texture of velvet on a moving sphere of liquid metal. You can't. Text fails to capture that kind of visual imagination.
And that's exactly where this multimodal vision language, this MVL paradigm, comes in.
It's the solution. It basically says, okay, text is the semantic skeleton.
But we need these explicit visual signals to add the flesh, the detail.
Yes. MVL builds this unified input. It combines the natural language with those very specific visual cues. But here's the really critical part. By unifying these signals, the model starts to actually infer what the user wants. It's not just following the text prompt anymore. It's moving beyond rote generation.
So it's not just following instructions. It's sensing creative intent. That's a huge leap.
It is. Once the model can cross-reference what you said with what you showed it, it can make connections and apply knowledge you didn't even think to prompt for.
Okay, so to process that kind of intent, you obviously need a pretty sophisticated engine. Let's break down the three main components of the Kling-Omni system.
The first one, and you could argue it's the most important for the intelligent part, is the prompt and answer, or PE.
Okay.
The best way to think of it is like the AI's super organized secretary. It takes all the diverse, often messy user prompts, the MVL inputs, and it maps them onto this clean, consistent data distribution before the generator even sees them.
So it's doing more than just spell check. It's inferring intent, it's preserving identity from a reference, maintaining spatial coherence, and even improving physical plausibility.
Yes, exactly. Improving physical plausibility through textual reasoning before generation. So if you ask for a glass cup shattering, the PE makes sure the generation will follow the basic physics of shattering glass.
That's fascinating. How do you even train a model to do that?
It's a two-stage process. They start with supervised fine-tuning, SFT, to build that foundational reasoning chain, thinking process.
That's them.
Then they hit it with reinforcement learning, RL, using a reward model that's designed to maximize factual correctness, richness, and semantic plausibility. That's how they bake the real-world knowledge in.
So RL for objective plausibility, not just, does this look good? Okay, so after the prompt enhancer works its magic, The request goes to the Omni-Generator.
That's the workhorse. It's a diffusion transformer that processes the enhanced visual and textual tokens together in a shared embedding space. That unified architecture is what guarantees the consistency.
Got it. And for the final polish, the cinematic quality, there's the Multimodal Super-Resolution, or MSR, module.
Right. The MSR is the high-end upscaler. It's a cascaded diffusion framework that refines all the high-frequency details, but it's constantly being conditioned on the original MVL signals.
So it never loses sight of the user's initial intent, even during upscaling.
Precisely.
The whole training process for this seems incredibly well thought out. They start with this huge pre-training phase.
Yeah, on massive text-video paired data to build the basic capabilities. And they infuse image-to-video tasks early on to create that cross-modal synergy right from the start.
And after pre-training comes the supervised fine-tuning, which has two goals.
Two main goals, yeah. First is continue training, which is all about aligning the model with those really complex MVL inputs like reference generation and editing. The second is quality tuning, where they use this super high-quality, meticulously annotated data set to just push the visual aesthetics to a higher level.
Then for the final alignment with human preferences, especially for motion, they use reinforcement learning again. But they chose direct preference optimization, DPO, over other methods. Why is that significant?
It's all about efficiency. They picked DPO because it avoids the really computationally expensive trajectory sampling you need with something like GRPO.
So they get the quality boost without breaking the bank on training costs.
Right. And the objectives are focused on what humans notice most. Motion dynamics, does it move correctly? And visual integrity, does it look right? It's all trained on human preference pairs of optimal versus suboptimal videos.
Smart. Okay, let's switch gears to the optimization side, because this is where the paper gets really impressive for the technical audience. That 15x inference speedup is a monster achievement.
It's the difference between a research project and a usable product. Going from 150 NFE to 10 NFE is what makes this practical.
So how do they do it? Let's talk about the first stage of that two-stage distillation.
Stage 1 is trajectory matching distillation. And the key thing here is that the student model is trained directly to execute in the target 10 sampling steps.
So they're not gradually reducing the steps.
No, they're going straight for the goal. The whole point is to make the student's 10-step generation trajectory match the high-quality teacher model's trajectory as closely as possible.
And then stage 2 refines that even further with distribution matching distillation.
Correct. Here, they distill the student to perform few-step ordinary differential equation, or ODE sampling. They note in the paper that ODE sampling just works better for these kinds of video tasks than stochastic methods.
And they keep the trajectory matching from stage 1 as a kind of guardrail.
As a regularization mechanism, yeah. It prevents the model from drifting away from the teacher's quality during this final optimization step.
The efficiency hacks didn't stop there either. The Multimodal Super-Resolution upscaler got some really clever tweaks.
Oh yeah, upscaling video is incredibly computationally heavy, so they swapped out standard full attention for local window attention.
Which can sometimes limit the model's overall view of the scene, right?
Yeah. It can, but they get around that by using a shifted window strategy in the odd-numbered layers. It's a pretty classic technique to get global awareness with local efficiency.
But the real genius move here, I think, was introducing asymmetric attention. Can you break down how that works?
The core insight is simple. In a diffusion process, your condition tokens, your text prompt, your reference images, they don't change from step to step. They're static.
Right. Only the noisy image latents are changing.
Exactly. So with asymmetric attention, the static condition tokens use self-attention, but the noisy tokens attend to the full sequence. The magic is that you can then cache the key value features of those unchanging condition tokens.
And reuse them for every single sampling step without recomputing them.
Precisely. For a user, if you're feeding in a whole library of reference images or a long video clip, this cache provides a massive speed up, around 2x, with basically no quality loss.
It's a brilliant way to solve a huge memory and computation bottleneck. The training infrastructure itself also sounds like a custom-built beast.
You have to. When you're training models this large with varied inputs, short texts, long videos, you run into massive network congestion.
So how did they manage that chaos?
They used a really robust parallelism strategy. A big part of it was microbatch level elastic Ulysses parallel switching and this two-tier all-to-all strategy. First intranode, then internode. It just gracefully handles the network traffic.
And on the reliability front, a 97% effective training time ratio is That's unheard of at this scale.
It's incredible. It comes down to things like automated fault detection and custom sync layers that allow for sub-minute restarts. When every minute costs thousands of dollars in GPU time, that's essential.
Okay, let's get to the fun part, the performance and the capabilities this thing actually unlocks. The human evaluations against the top competitors were pretty damning.
They were. For video editing, Kling-Omni against Runway LF got a GSB score of 230%. It just dominated, especially in dynamic quality. The motion was rated good 61% of the time, which means it just looked more natural and physically plausible.
And against VO 3.1 on image referencing tasks, it was even higher, 247% GSB. And here the big wins were in visual quality and identity consistency.
And that identity consistency is the holy grail of video generation, keeping a character looking like the same character frame after frame.
Which leads us perfectly into the qualitative features, starting with multidimensional precise referencing. This is way beyond just using a single image.
It is. You can use images, video, text to define not just a subject, but its style, the shot composition, specific actions. And the key to the identity problem is what they call the subject library mechanism.
How does that work?
It's such a smart approach. Instead of giving the model one photo and hoping it gets it right, you give it a library of images of the same subject, different poses, expressions, angles.
So it builds a much more robust, multifaceted idea of the subject.
Exactly. And that leads to incredibly stable identity preservation, even in really dynamic scenes.
And you can see that power in the high degree of freedom interactive editing.
Yeah, we're talking way beyond just adding or removing things. Kling-Omni can do complex stylization, like turning a whole scene into a Ghibli animation or an origami world.
Or attribute manipulation, like changing an object's material to glass or freezing a waterfall.
And because of that unified MVL input, it can handle flexible pass combination. You can throw a complex multi-part command at it all at once.
Like change the background to a snowy mountain, put the character in a spacesuit, and make it look like an oil painting, all in one go.
Which is a huge workflow improvement. You avoid that accumulation of errors you get when you have to run 3 separate editing steps, one after another.
Finally, let's touch on the exploratory features, because this is where it starts to feel less like a tool and more like an intelligent partner, the reasoning-enhanced generation.
This is where that prompt enhancer really shines. It uses its reasoning engine to ground prompts in real-world context. They call it leveraging world knowledge.
So like the GPS coordinate example.
Yeah, you give it GPS coordinates, it decodes them, retrieves knowledge about that landmark, say the Eiffel Tower, and then generates a scene that's actually contextually and geographically aware.
Wow. And it even shows abstract reasoning, like figuring out how to sort objects or complete a puzzle. It's actually thinking about spatial and semantic relationships.
It is. The model is moving past just depicting what you described to actively understanding and solving the problem within your prompt.
So wrapping this all up, what's the big picture here? Kling-Omni feels like a truly foundational step forward.
It is. They've replaced that old fragmented expert model approach with a holistic unified system, and it's all built on the MVL paradigm and backed by this incredibly efficient distilled infrastructure. They've shown a clear path for scaling up generalist video intelligence.
The real takeaway for me, though, isn't just the architecture. It's the paradigm shift that MVL represents.
I agree. If a model can create video based not just on what you type, but on complex visual cues and its own inferred intent, it opens up a fascinating question. What are the limits of creative control when the model can generate context you didn't even explicitly ask for?
That's the provocative thought to end on. This shift from just literal prompting to true multimodal intention inference, that's what makes Kling-Omni a genuine watershed moment for the entire field.